I'm going to talk tonight about applied Bayesian networks because I believe that Bayesian networks are a really good introduction to the broader topic of machine learning. When we were here in December, there was a lot of conversation around like even being able to agree on a definition of what machine learning was amongst the people who were here, and I think it's kind of a very broad and sometimes intimidating topic that can be difficult to sort of get a mental foothold in, especially because a great deal of it is within the academic realm and is often sort of couched inside papers that are unfortunately written to be over verbose because that's sort of a criteria in order to get pitched. So I do think that there's a lot that can be unpacked in sort of at the practitioner level. Like if you're not looking to push the boundary of what we can do today with machine learning, but you just want to know the toolkit and be able to apply it to a given business problem, I think that's really accessible and possible for pretty much anybody. So the way I'm going to do that is by talking through a real problem, something that my team has done at my job. And then giving a little bit of the formal underlying material, enough to understand the internals, and then I'll give you a little live demo of it working in real life. So let's jump in. Before I go any farther, I'm going to give what I think is my favorite definition of what machine learning is, because I think what with the advances being made all the time in playing Go, and driving cars, and being able to do audio processing and natural language processing, this idea there that like those things that are hard or that you could never think of doing without some sort of very deep statistical model, those are machine learning, and everything that's very understandable is not. I don't think that's fair. I think it's more accurate to say that a program is learning if you're not explicitly giving it a set of conditionals, but instead you give it some amount of experience to learn from in the guise of data, and the more you give it, or the more good data you give it, the better it performs given some sort of evaluation metric. So, for example, if you're trying to classify pictures of hot dogs and pictures that are not hot dogs, for example, then if you have given it no pictures and it just classifies everything as a hot dog, then that's pretty bad. But you give it a few pictures of a hot dog, and it can find ones that are sitting just on a plate and not the rest of them. That's a little better. We're going to talk about a specific, more abstract case here in a minute. But the general idea is, if you have some sort of system, even if it's just one that's calculating like means and medians, but that's giving you better results against the metric that you really care about, that's still learning. That's you not having to program, but just adding more data, and the system gets better. All right, let's talk about my business problem first, and then we'll go into a good model for solving it. So here's the problem. I work at Udacity. This is a place where we have many different sort of small credentials that are targeted at vocational disciplines. Things like machine learning, data science, robotics, and like web development, DevOps, mobile, like all these things have their own directions that people can go in. But within specifically this sort of what we think of as the school of AI, our data track, there are many different levels of places people can start. There's an introduction to programming credential, there's sort of the data analyst level, there's a machine learning nano degree, there's an artificial intelligence nano degree, and each one of those sort of, you could imagine them being linearized, although it's not quite fair. There's a great deal of overlap, and in some cases there are things that you would need to know to be a data analyst, SQL and Excel, that you might not really need to know for applied artificial intelligence. That people who are good at it might have never built an Excel workbook in their life. So it's not necessarily truly linear. But we do know that many people come to Udacity or to really any online education platform. They may not know exactly like what they would be good for or what they would fit into. And if you just let them pick themselves, there will be a lot of bias that comes to that. Some people who have very little self-confidence will simply say, I should start at the very beginning no matter what because I'm not very smart and I don't know anything. And they may drop out simply because they get bored or feel like that the material is just so repetitive. That may be a symptom of the fact that they actually knew a great deal, they just weren't very confident. Likewise, you might have somebody who's quite ambitious who feels like, I can just jump down here to the top level, I'll see what I don't know, and I'll dig into the things that I don't. And if they become overwhelmed, they're unlikely to diagnose that as being, maybe I should have started simpler. They're likely to diagnose it as being, this content is terrible, who could learn from this? So like slotting someone into the right place is actually pretty important for our ongoing business, because people who successfully complete one degree are, first of all, that proves that our business is working, and second of all, that means that they're more likely to say, you know what, I could do another one of these. So there's a great deal at stake in making sure that people are well fit to the curriculum that they end up wanting to go through. So how can we deal with this? You could just let people choose themselves, and that's broadly what happens. But we talked about some of the problems that are present with that. You could takes some sort of prerequisite analysis. And in fact, there already have existed many things like this. For example, in order to do machine learning effectively, it's helpful to know some foundational calculus and some foundational linear algebra. You don't need to be an expert in it, but having a little bit of an intuitive grasp of how those fields of mathematics work is helpful. And if you don't have it, it's not hard to get. But it's also, you're also likely to have a bad time if you just jump straight into the curriculum. So you could give people tests on things like, little quizzes on things like discrete mathematics and linear algebra and calculus. And based on how they do there, you could say you're a good fit for this or not a good fit for this. And then the question you might ask is, well, how would we know? Like, you can't just say they got all the questions right, because like even somebody who knows things quite well might be confused by one of the options in a multiple choice set, or might slip and click the wrong one by accident. Like, there's some sort of soft assignment that's present there, and it'd be hard to just draw a threshold by hand. You could do it. You could say if you get more than half of them right, we think you know that topic. But how confident are you that that's a really good representation of the latent knowledge that person has? So that's not necessarily a great solution, although it's better than nothing. You could also, this is probably the best one from in terms of accuracy, you could have an academic expert, somebody who knows the curriculum very well, or some set of people who know the curriculum very well and who know the sort of signals that people give off, interview everybody who might take one of these and like give them a bespoke one-on-one and help them, like kind of a guidance counselor, decide what direction they should go in. The problem is that would be incredibly expensive for the sort of price points that are present here. Maybe if you're Stanford, you can do that because that if they come, they're going to give you a lot of money. But when you're talking about like online education level revenue, that's not something that's like, that might be really good for the student, but it's not going to make the business last very long. So the foundational problems with a business problem like this are that it's not clear cut. There's a great deal of uncertainty that's present in it, and even when you get some information about that person's latent knowledge, it's not, like there's a little bit of noise in the signal. You could guess and get a question right that you actually didn't know very well. You could misclick and get a question wrong that you actually did know the foundational material pretty well. So it's not a clear channel. Additionally, there's a great deal of complexity. Like in order to cover all the many topics that could be reasonable prerequisites to each one of those bits of different curriculum, that could be a lot of questions. And do you really think someone's going to go through a 200 question survey before they sign up for your online education product? Probably not. Or at least if they did, they probably don't need your online education product. They probably got the determination to go like read Wikipedia until they get it. So how could we, like, it would be worth it to take a moment and think about like how would you solve that? Because there are a lot of good answers that don't involve having to open up like a complicated toolbox you don't understand the internals of it and apply it to it. I think a really good start is like give them a few questions from each subdiscipline and like do a hard threshold. If you give them 4 questions that randomly chosen from each topic, and if they get more than 2 of them right, say they've got that one, and then assign them based on the most difficult curriculum of which they got the majority of the component topics corrected. Like, that's an okay way to start. Let's talk about a better way. There is a class of machine learning models. Now, models in general, like that's sort of an abstract term. What's meant by that is some sort of algorithm that represents the underlying state of a problem fairly well. So you might be familiar with linear regression if you've ever taken a statistics class, where you have a bunch of points that have some input variables that sort of tell you where along a known variable that point lands, and an output variable that is like something that should be related to it. A good example, a common example in machine learning literature would be something like, given the size of a house in square feet, could you guess at the price that it would sell for? Now that doesn't contain all the information about a house, but if you were to plot it, you would see, something like this, right? Like these plots would all sort of go in an upwards line, right?
Around here in 2012, $125 per upstairs finished square foot was kind of the sweet spot, and the finished basements didn't count.
And so you could think that like this is a model. This is a way that like if you drew a line that minimized the distance between that line and all the points around it, then you could say, well, if I was given a new data point, I could just pick the one on that line, and that would be pretty close. Now, there's nothing opaque about this, right? Like this is a fairly simple thing to understand, and that is one instance of a model. In this case, 2 variables that are fairly well correlated. A line models that relationship pretty well. Most machine learning models are a little more complicated than that, but this is still one, right? If you add more data to this, it gets. If you add more data to this, it gets better. This is like linear regression is still, if you continue to add to it over time, this is still could be thought of as a machine learning solution. The class of models that I want to talk about for this particular problem are called probabilistic graphical models. Now, that already is a bit of verbose terminology, but we can pick this apart fairly easily. Probabilistic means that instead of dealing with like discrete ones and zeros, that we're talking about probabilities. That's no worse than saying like, you know, if someone gets 3 out of 4 questions in linear algebra right, what's the probability that they're pretty good at linear algebra? 75% is a pretty reasonable guess. They got 3 out of 4 right? Graphical, this is not in the sense of this kind of graph. This is graphical as in a graph theoretic model or a representation that can be encoded with nodes and edges, right? If you've ever seen any sort of problem modeled like this, where you've got a bunch of things that are discrete entities and then lines driven between the ones that are connected, that's a graph, okay? There's a lot of foundational theory that goes underneath it, but ooh, gosh, that's a really bad marker. But the point is, like, this is a really useful way to draw things and internalize them in your brain, find a mental hook for them. This is not to say that you necessarily have to like have objects in your code that are nodes and edges that go between them, but that this is a good way to think about a problem and sort of decompose it. So probabilistic graphical models are graphs, sets of circles and lines between them, in which nodes represent random variables or things that you can assign reasonable probabilities to. We're going to see an example, so just bear with me. And the presence of arcs or edges between them represent causal relationships. So we'll see an example in a moment. And if there's not one there, then we assume that those two things are independent, that one does not cause the other or that they don't relate to each other. Hence, you get a compact representation of joint probability distributions. We'll talk about what that is. But most importantly, they provide a natural tool for dealing with two problems that occur throughout applied mathematics and engineering: uncertainty and complexity, precisely the two problems we have here. Data sets where we might not have all the data filled in, or where there might be latent information not well represented by the data set, and situations where like the total number of inputs is very high and resulting in a lot of complexity and higher dimensionality. So let's look at a very simple example. And hopefully, if we look at this and then go back to the prior slide, things will make a little more sense. This is a graph. It is a graph that represents what may happen in any given day in your lawn. It may or may not be cloudy today in the morning. And your sprinkler may or may not go off today, depending on many things. First of all, whether you scheduled it or not. Second of all, what season it's in. And third of all, sometimes people turn their sprinkler off if it's raining. It may or may not rain today. Some days it rains, some days it doesn't. And some days your grass is wet around noon, and some days it's not. Now, all these things happen sometimes, and they don't happen sometimes. And if you were to ignore all their relationships, you could still get an idea probabilistically of when each one of them occur. In this case, there's an explicit assignment here that says it's 0.5 cloudy, 0.5 not cloudy, right? Or if you look at maybe a year of data, half the days it's cloudy. That's fairly easy to understand, right? If you were then asked what would you predict for a given day on the calendar, not knowing anything about the weather in the surrounding days, then you might not be able to guess very cleanly between them. But it wouldn't be too bad to just flip a coin and say, you know, whatever happens, that's whether it's cloudy or not. Now, some days your sprinkler goes off, and some days it doesn't. Perhaps in an area that's hot like Columbia, maybe most days, if you sample over an entire summer. But some days not, right? And if you didn't know anything about the rest of this, you just had the data from a summer across your yard, it wouldn't be crazy to say, if you pick a random day and wanted to predict whether or not your sprinkler went off, you could say yes most of the time and be right, if it would, like, given some condition. Same thing for rain. You could look at all the days over the course of a year that it rained and it didn't rain, and that would give you a reasonable probability distribution. If it rained a fourth of the days, then saying a 25% chance of rain if you just pick a day at random, that's not bad. So each one of these could be thought of individually, but when you relate them, you start to be able to do better. If you know whether or not it's cloudy, that can help you make a better prediction about whether or not it's going to rain today, right? This is called a conditional probability relationship. If you know that today is cloudy, you're going to make a higher confidence guess about whether it's going to rain or not than if you know it's not cloudy. That's represented in this particular diagram as a conditional probability table here. Given that it's cloudy today, the probability of it raining is 80%. Given that it's not cloudy today, or there are no clouds, the probability of it raining is much lower, 20%. Right? Now, that still may mean in the aggregate that if you look at all the days, that's still 50%. Like if you didn't know anything about the cloudy structure, you'd have to say, well, half the time it rains and half it doesn't. But if you know there's clouds, you can do better. right? Same thing with the sprinkler. If you know that it's cloudy, then you can say that it's very unlikely the sprinkler is going to go off. That bit of information gives you a much better prediction. If you just take all the days where it was cloudy in the morning, how many days did the sprinkler go off? Well, that's going to be far fewer than if you just look at all the days where it's not cloudy. If someone has an every other day schedule, then half the time it's on and half it's not. But they turn it off when it's cloudy. All of a sudden, that lets you make a better prediction about this variable based upon what you know about a different one. Now, wet grass here at the bottom. What's the probability of your grass being wet if the sprinkler didn't go off and it didn't rain? Well, here that's 0. There's nothing to make it wet, excluding dew or random water trucks flying by and throwing things off. Incredibly low probability events, but effectively 0 for the case we're modeling. If you know that it both rained and that the sprinkler was on, both things are true, then you can say with very high confidence that the grass is going to be wet. This is an example of how knowing information about some variables that are sort of probabilistic in nature, being able to observe just a few of them, can begin to give you better information to make predictions about some that you assume are related, right? So this is a fairly simple Bayesian network, and the Bayesianness of it just has to do with the fact that it uses the Bayesian chain rule for modeling conditional probabilities. So that's not important. I encourage you not to spend a lot of time thinking about the terminology, but instead to really grasp the intuition that when you can model many different events, that you can know the marginal probability or the odds of it happening in its isolation, but that when you relate them, you can often do much better by taking a subgroup based upon something else that you observe. So even if you can't go home and see whether your grass is wet right now, you can, knowing some other things, make a pretty good guess. Okay? This is what we would like to do with something like our student problem. We may not be able to actually know what the latent state of their brain is, or what would truly be the best nanodegree to assign, or the best credential to assign them to. But given some information about them, we can begin to make a pretty good guess. That's the intuition. Okay.
Like people who make jokes about language as such are probably going to be happier computer programmers than people who don't.
Sure, that's a good example. Perhaps you can see now that this is a probabilistic graphical model because it is both a graph and each node is represented with a probabilistic assignment, right? So both of these things, I guess the question is, how do you make one of these, right? The answer is actually surprisingly simple for cases like this. It is possible to elicit both the structure, that is, what nodes exist and how they are related, and the probabilities that are assigned to them simply manually. It's not unreasonable to say, I'm going to make up some nodes and assign some probabilities to them because I'm familiar with the underlying domain to some extent. And expert elicitation for Bayesian networks is not an unreasonable way to start. So for example, to give an example of this, I have created one for us, which we're going to look at right now. If I can get the Chromecast to broadcast my entire...
There we go.
Did I get my... No. What I really want it to do is cast my entire desktop. Here we go. I think I got the whole thing this time. All right, so let's go here. This is a sort of an academic tool that gets presented in one of the courses that I'm going to give you as a resource later on. For now, understand that the idea of this tool is to be able to let you quickly model these sorts of networks manually and be able to play with running inference through them. So we're going to model the likelihood that someone shows up to DevComo in a given month. We're going to try to predict that. Now, I built this based on data that I had in my head from December, and given how many people showed up today, I think it's fair to say that my estimates are a bit low. But I think we'll still get the point. Oh. Dragging this hard. Okay, so look at some of the nodes I put in here. Some things that we could represent probabilistically. Whether or not someone has children, whether or not they work from home, whether or not they're sick today, whether or not they have a child care problem today, whether or not they're speaking today. All these things are things that I think are related to whether or not they show up. Now, I don't have any data. This doesn't go back forever. I don't have a spreadsheet that shows all the times all of you showed up. So this is entirely based on what my gut feeling is about each one of these probabilities. It's not a great way to start. You could do a much better job by actually having a little bit of data and making informed probability assignments. But even this, I think, is going to be pretty good. So I'm going to show you what it looks like to do a query through all this. Right now, all of these variables are unobserved. And what that means is that we haven't instantiated any particular case of it. Each one of these just shows the marginal probability of each one of these events, considered in isolation, unrelated to any of the things that are happening. What's the marginal probability that someone shows up at DevComo in a given month? About 61%. Apparently I should have made that higher. What's the marginal probability that someone has children? I guessed 75%. We live in the Midwest, so there are some younger people here, but I sort of guessed that most of us would have kids. Probability to work from home. I don't know how common that is here, so I assigned it 35% because out of the number of people that I knew, 35% of them work from home. So that may or may not generalize. But more important than each one of those arcs, or than each one of those nodes, are the lines I've drawn between them. Because those represent conditional probabilities that I think are accurate. For example, working from home, I've set this up as a root node. There's nothing else that's pointing to it. So I've just sort of set that up as a probability on its own. It's completely uninformed by anything else. 35% chance you work from home, 60% chance that or 65% chance you don't. But what about is sick? Some of the things in this graph are going to change whether or not it's likely that you get sick or not. I'm actually going to show you the conditional probability table here that I've picked. You can see here that the two nodes that point into is sick are whether or not you have children and whether or not you work from home. My intuition is that if you have kids, obviously you're going to get sick more often. I do. They are like built to be disease vectors. They catch everything and they bring it home to you. If you work from home, that means you don't go to an office every day, which can have some amazingly protective effects in the winter, because no one else touches your computer but you. So I believe that if you work from home, you're less likely to get sick. Therefore, given that someone who does not have children and who does work from home, I think it's extraordinarily unlikely that they're ever going to get sick. Whereas if they do have children and they also work in an office, then I give them a 30% chance, a 30% estimate of them being sick on any given day. Now, whether or not these are accurate is not really important for this example. What's important is that you can see how these things are balanced relatively, right? The more things you know about nodes that influence it, the better prediction you can make. So let's actually elicit a query. Let's observe one person. Now, when we say observe, that means that we want to take a given, this is our model that generalizes. We want to take one case and observe that actual case. So we're going to observe me. Now, do you know whether or not I have kids? Well, I already told you, right? So do I have kids?
3.
Yes, that's right, 3. So let's go ahead and mark that I have children. Now, what just happened when I clicked that? Did you see the probabilities update everywhere else? Yeah. The only thing you know about me is that I have kids. But already we're less confident that I'm going to show up. Right? That influence flows through many nodes on the graph. Now, not to all of them. You'll notice that didn't change anything about whether or not I'm speaking today. There's no causal relationship modeled there. I didn't draw any other edges there. But the ones that influence is drawn through, they all updated when we just knew one thing. This allows us to reason with about uncertainty very powerfully. It means that even in cases where we only know a little bit, we can do better than a marginal guess. So what things went up? A childcare problem. Yep. If you don't have kids, you have a 0% chance of having a childcare problem. So I have a higher one now. What else do you know about me? Do I work from home?
Yes.
Yeah, some people know that. Okay, well let's observe that as well. So we've observed 2 variables. I work from home and I have kids. Now my likelihood's gone back up again, primarily because my chance of being sick has gone down because I don't work in an office, right? Now, what happens when I observe that I'm not sick? Well, then my probability of being at DevComo goes up a lot more, right? A lot of what the relationship between having kids and working from home was here is really related to how likely I am to get sick, right? And so when you know that I'm not sick, these begin to matter less. In fact, if you know that I also didn't have a childcare problem, I've got a quite high chance of being at DevComo. And now notice what happens if you don't know these other things. So this didn't really change, right? Why? Because I observed the 2 things that were really, regardless of anything that comes before it, if you know this information, that's the big driver, right? So these relationships across the graph do exist, But when you find things out, that breaks the influence of other nodes. It's kind of like saying, is my grass wet? Well, I know that it rained today, so it's likely that it's wet. Now, even if I don't know whether it was cloudy or not, does that change my estimate of whether it's wet? Well, no, because I know that it rained, right? That was the proximate, more important variable. Okay, so I think that gives a point to like how these can operate. Now for when you're training these, it's really useful to have like sets of data where you know all the variables for many people. But even without knowing all of them, you can still do a pretty good job. And when you are reasoning in domains where you might not get all that information about a new prediction you need to make, this is a really powerful way to do it. The more data you get, the better prediction you can make. But you can start to make a better than random prediction as soon as you know one of the input variables. Okay. So let us return to our presentation. Stop. I want to cast just my tab. This is my first day using a Chromecast. I love it. Okay, so let's go back. I want to note some things about this. So in this case, this was a network that we elicited from experts. Or from amateurs. In my case, I made guesses at each of these, but I think you can see how it hangs together. Now, the better we can make those estimates of the probabilities inside the model, the better it's going to perform on real data. But I want you to notice some things about this network. So this is what we just looked at. You saw how evidence breaks or how influence breaks when you know intermediate evidence, right? Like when we turned on the sick node, then it really doesn't matter whether I work from home or not. The important thing for predicting whether or not I'm at DevComo was whether or not I was sick, right? This sort of influence bouncing around works pretty obviously in that way, but there are also subtle ways that it works in. For example, if you know that I'm sick, that's the only thing you know. You don't know anything else, but you know that I'm sick. What does that tell you about these nodes? If you know that I'm sick, am I more or less likely to have kids?
More.
That's right. Your inference doesn't run one way. Knowing something about one of these variables doesn't only impact your target variable. It actually allows you to make inferences about the rest of the graph too, at least the ones it's related to. But now, if you know that I'm sick, how likely am I to work from home? More or less? Less, right? Because we know that if you work in an office, you're more likely to get sick. So knowing that I'm sick makes it more likely that I work in an office. But watch what happens here. Usually we've been seeing influence only flow down these arrows, right? What happens if you know that I'm sick and that I have children? Like, if you just knew that I'm sick, then you start to say, well, maybe he doesn't work from home. But as soon as you find out that I have kids, that's a pretty good explanation for why I'm sick, right? That erodes any confidence you had about whether that indicated that I work from home or not. This is an example of what's called explaining away. When you have these structures where multiple nodes have a causal influence on a downstream node, then knowing one of them explains that state often well enough to sort of eliminate the inference you're able to do further up. So as you observe whatever you can, sometimes it's not obvious the directions in which influence from one variable to another can flow. Now there are like rules that you can learn to understand how it bounces around. So it's called playing baseball, as you bounce a ball of influence around the graph and understand how one thing affects others. And it can be learned, but it's not really important to grasp those rules right now. What's important is to understand that these things impact each other and that observations can represent breaks in influence or can also represent new pathways of continuity. If you just know that I work from home, that doesn't tell you much about whether or not I have children. But if you know that I work home and I'm sick, that like removes anything that being sick told you about having children. So each one of those observations can change how influence spreads around. It's possible to do both diagnostic reasoning in Bayes nets, that is where you have something that you know the outcome of and want to know what caused that outcome. So, for example, if you know that I didn't show up and I'm not speaking, like I wasn't scheduled to speak today and I didn't come, that begins to tell you things about like further up in the graph, right? That allows you to diagnose the cause of those observed effects. If this were a graph that represented illnesses, then the fact that you know I have cancer, lung cancer, might tell you something about whether or not I'm likely to smoke, right? That's a diagnostic, an example of diagnostic reasoning. The nice thing about Bayes nets is you can, knowing one thing, reason about other areas in it. So you don't always have to use the same target variable. You can also do causal reasoning, where you know many things about me, and then can make a prediction on what's going to happen. If you know I don't have children and I do work from home and I am speaking today, it's extraordinarily likely that I'm going to show up. This is an example of working the other way, saying I know some causes, being able to predict the outcome or the thing that we would diagnose. Now, this is all cool, but this is all stuff that we've like elicited manually. Like the claimed topic here is we're going to talk about learning. So how do you learn something like this? Well, there's different pieces to learn. One are these probability distributions, right? Like how likely are you to have children? How likely are you to work from home? How likely are you to be speaking today at DevComo? And then how likely are you to be here? Those relative weights of those probability distributions, that is something that can be learned. It's also possible to learn the optimal structure, or that is, given a bunch of nodes, to learn the optimal set of arcs between them based on probability observations. Now that is a much more complicated topic, and I don't really want to get into it today because you can often do a pretty good job by starting out with a manual known structure that you just sort of build from expert experience, and then learning the interior conditional probability distributions. That's a really good way to start. What structure learning has to do with is essentially saying, given I have these nodes, and I can produce a model that is accurate to a given degree, if I change the structure, can I make it more accurate? And there are many, if you're familiar with search algorithms, many of those are applicable in this case, where you could say, you could do basically like greedy search, where you could like add or remove one arc at random, and then see if it gets better. If it gets better, keep that one, and then try to add another one. Or you could say, if it doesn't get better, like go back to my original structure and try a different direction, right? There are many sort of ways to do pathfinding through the space of all possible models, but that's not something I want to cover today. Instead, let's just think about how to learn the probability distributions inside each of those nodes, or how likely each one of them are given information about them. There are sort of two cases that you can split this into: full observability and partial observability. Full observability means that you have a data set that represents the thing you're trying to model, and every single node has a value filled in for every record in your data set. If we were building our DevComo net, then what that would mean is having some sort of tabular data that recorded everybody's attendance and absence back for a given period, maybe a year, and also all of these values for them in every week. So like every record in there has information about all of these. That gives you a really straightforward way to learn the probabilities of each one of those nodes, and I'll show you how in a minute. The other possibility, partial observability, is where you know some of these things about each one of those rows, but not all of them. You might think that like we should just throw all those out if we don't have all the information in them, but we can actually do a pretty good job of squeezing all the info we can, even out of records that are missing data. And you might even have some intuition already about why that is, given what happens when you observe only some things, right? Spoiler alert, if you observe these three things, you can be very, very confident about whether I'm sick or not. And so even if that value is missing, it's possible to make some sort of good guess about what's likely to be there.
It sounds like this is where playing baseball is competing as maybe a better solution than linear regression in some cases. I remember more than 6 variables makes your regression model look great and work worse in real life.
It'll at least look very good on your training set, right?
Right.
And not generalize very well.
Exactly.
You're describing overfitting,
Right.
which is a common problem for complicated models. That is one of the nice things about a model like this, is that you don't have to have like a very dense data set where everything's populated, and you can like do a pretty good job of reasoning about a large number of variables without like having them have a lot of interactions with each other. You can make independent assumptions. That being said, it is possible to overfit. Pretty much every model that exists has a possibility of overfitting, or doing a really good job of predicting things that are in your training data and not generalizing well when you try to apply it to the real world. There are a lot of techniques for dealing with that, but I'm going to kind of leave it on the side for the moment. So let's talk about the full observability case. The case where every bit of data that you have, or every row of data that you have in your data set has all the variables filled in. So which means that you have access to every bit of probability, or every bit of information to inform your probability that's possibly available. It might look something like this. This is for our little, is it cloudy, is it like our weather net, I guess is what I'll call it. This actually is not mine. This is like a very common introductory example in Bayesian texts. This whole cloudy, sprinkler, rain, wetgrass. Almost every introductory tutorial about Bayes nets includes this one. Common reference example. Something that might be used to inform this would be something like this, where you can, maybe there's a date out here, so these are all dates in order, or it doesn't necessarily matter as long as they're accurate, but you can imagine each one of these being a different day at my house. for example, and saying on day 1, it was cloudy and it rained, and I had wet grass, and my sprinkler was never on. That's one training row, right? One example. Day 2, it was not cloudy and it didn't rain, and my sprinkler went on, but it all evaporated so fast that my grass was not wet when I went out to check it. And each one of these, you can sort of imagine what the example is that informs that. Now, how could I take this and learn the best distributions for each of these nodes? And like, don't just wait for me to give the answer. Like, think about that for a second. It's not a hard problem. Right? Let's start from the very beginning. How can I figure out this root node, cloudy, that has no other inputs? How can I figure out the probability whether it's going to be cloudy or not, without guessing, like using the data set?
Just find the average.
Yes.
How many days were cloudy divided by the total number of days?
Exactly. To compute the exact marginal probability, right? Add up all the days it was cloudy, divide it by the number of days you have. That is the probability that any given day is cloudy, knowing nothing else about it, right?
5/11.
Yeah. What's that?
5/11.
Yeah, well, in this case, yes. Actually, I think it's 5/10 because the first row is titles. So this doesn't get to count.
Oh, you're right. You got it.
Yeah.
Right.
Good. So yeah, in this case, it actually lines up perfectly. Yeah. Now, that one's fairly easy.
So your spreadsheet matches the numbers in the cells.
In this case, I make no guarantee about that happening for the rest of you.
Okay.
But like in this case, yes, this would be a correct elicitation of the underlying probability, right? I looked at how many days we had in total and how many of them were cloudy, and I assigned that as the probability distribution for that node. Now, what if I wanted to figure out how likely I was to have the sprinkler on or not? Now you might say, well, we can do the same thing. I'll just add up all the days the sprinkler was on, and I'll divide it by all the days. But that's not quite right in this case because we're not asking for a marginal probability. We're trying to find the conditional probability given something that we know whether or not it's cloudy. So how could we compute our sprinkler node?
Where cloudy is equal to 1.
One.
Then look at
Yeah.
all those and do the
You only
average of
use
that.
those rows.
Yeah, that's literally it. Take your subset of days where it's cloudy, count up the number of days in there that the sprinkler was on, divide it by that number of days, and that is the probability of the sprinkler being on, given that it's cloudy. And of course, because probability is most total to 1, the inverse is 1 minus that probability, so 90% the other way. And then take all the days where it was not cloudy, where cloudy was false, and add up the number of days that the sprinkler was on, divide it by that number, by the number that where it was not cloudy, and that will give you that parameter. Okay. You can do the same thing for each of these. The more nodes that you have feeding into a given node, the bigger your probability table. So it's a little more tedious, but you still do the same thing. Like for this wet grass, given that the sprinkler is on and it rained, we'll take all the examples where the sprinkler was on and it rained, okay, and then count up how many days the grass was wet out of that subset, divided by the total number of days. That's your conditional probability. Now, that sounds stupid simple, right?
I think there's even a formula that takes a bunch of.
There is. It looks like that. We'll get to that in a minute. You're absolutely right. Yes. But all that formula is symbolic notation of that exact idea.
Right.
A summation and then a division, right?
So what you could do with this is the more rows you have in that spreadsheet,
the more
the more
accurate.
confident you are that the values you're guessing are within some delta of the true.
Sure. Now we could definitely say that we will probably never perfectly model the underlying data, right?
Yeah.
But there are model evaluation metrics. Like you can say things. First of all, like say I have 3,000 rows of data like this, 3,000 days. Oops. 3,000 days of data. I could train on all of it and then say, well, those are my probability distributions. That's not bad. But if you wanted to get an idea of how accurate you actually are, you probably wouldn't want to feed all your data into your training set. What you might want to do is withhold some of it. Maybe 300 rows at random. Take those out of the data set. Feed it the rest of them, and then try to predict the ones it didn't get to see, and see what percentage of those it got right for your target variables. That's a good way to evaluate how well your model generalizes. Go ahead.
Yeah, I'm just wondering, in the model there, you made choice, and I'm wondering if we go from we have I had to count the rows here, but if we notice the sprinkler is not out on cloudy days, would this model presuppose that the sprinkler is keeping the clouds away? Or would that have to be a different model?
No, you wouldn't necessarily say that it caused that, but even if it's not a causal relationship, you can still make a good inference, right?
Yeah,
Like-
I'm just wondering, the diagram you drew, the diagram that's there, is it presupposing that the decision to put the sprinkler out depends upon whether it's cloudy, or is that still open at this point?
Gotcha.
You need a different network.
So the direction here, that the arrow, that these are directed edges. This graph, there are such things as graphs that have undirected edges where they don't have necessarily a prime direction in them. But in these ones, you'll notice all the edges are arrowed, right?
Yeah.
And the idea is that you're modeling what could be thought of as a causal relationship. Now, not causal in the sense that that it is a direct, approximate physical cause,
Yeah.
but causal in the sense that this makes that there is either this makes that happen, or there is some underlying thing that makes both of these things likely to be true at the same time.
Correlation.
Yeah, now it is closer to true statistical correlation than it is to modeling direct causation, because we certainly would not say that the clouds being up there,
Yeah.
directly impact your sprinkler system unless they have some sort of light sensor built into them that make a decision about them. But it's not unreasonable to say that cloudiness impacts your behavior, and that you decide to go turn the sprinkler off when it's cloudy outside because you expect it's going to rain. And that's the sort of fuzzy causation that we're talking about here. There is something that happens that causes the sprinkler to be off it causes the sprinkler to be more likely to be off when it's cloudy. It shouldn't be confused with actually expressing actual direct physical causation. Not the same thing. Or even direct causation the way that you might try to elicit it in a statistical test where you're trying to determine the impact of one variable on another. Not quite the same. This is really modeling correlation more than anything else. But correlation can still give you good predictions even if you're not capturing actual probabilities. And we're going to talk in a little bit about hidden variables, possible underlying latent causes that you might not be able to model directly, but that may be the underlying causal agent in a given model. Now, there are still some problems with this. For example, we have an extraordinarily low number of dimensions in this model. There are only 4 variables to observe. So it is possible to have data that fills in each one of the possible combinations. But you could imagine a model that's much, much bigger than this, and has many more variables, and in some cases, nodes that have 5 or 10 causal links pointing into it. And in those cases, you may not have sufficient data to fill in every one of these cells appropriately. So there are sort of some algorithmic tricks that help you deal with cases where your data has the curse of dimensionality has struck you, and there are so many different cells you don't have enough data to fill in them all appropriately. There are ways to deal with that. But for now, take it as a relaxed problem that computing these probabilities essentially amounts to probability the way you learned it in grade school. Take the number of times that a thing happened, divided by the number of times it could have happened, and that is the probability that I had to fill in. Now, there is a formula for this, and typically, instead of trying to explain it intuitively, this is what you'll get. Boom! So what does this mean? Well, n is supposed to be your number of training examples. Okay, so the number of fit a given criteria for a given node. M would be the number of nodes in your graph, so going through each one of the nodes. And S and N are actually the same in this case. They are the number of training examples that you have. And then the log of the probability of a given state of X occurring, given X's parents, given that node's parents are the things that cause it, and the data that's available. This produces one number for the entire graph, right? Which is essentially a likelihood function. That is, how likely is this model to happen given all of the data? What you should be intuiting when you hear that is, given all the ways that I could assign probabilities to each of those, how likely is this particular data set? And what that means is that if I assign wrong probabilities to these and then multiply them all out through this formula, then I will end up having very large negative numbers. When I assign the correct probabilities, or the ones that manifest themselves throughout this graph, I will get the highest possible number, which will still be a negative number because you take a log of a number next to less than 1, you get a negative number. So you're adding up a bunch of negative numbers. But the closer this is to being a sure thing, the smaller that negative number is. So when you sum up a lot of small negative numbers, you get a negative number of small negative. If you end up picking very wrong probabilities that are off, you'll get very large negative numbers. Therefore, the correctly computed probabilities will maximize this likelihood function. Okay? And that is why this process is called maximum likelihood estimation, MLE. So when you see MLE as an abbreviation around Bayesian, that's essentially what it's talking about. Just computing conditional probabilities, okay? With some other tricks for cases where you can't fill them all in. Now, like I mentioned, this actually ignores the problem of data sparsity for low probability combinations. There are cool tricks for that. I'm not going to talk about them today. But there are ways to deal with cases where you can't fill in all the data. Now, this might not feel very satisfying because you actually didn't need to do any like sort of iterative optimization to arrive at it. And often when we see machine learning papers that are published, they're talking about things that have to churn for days and days to like fine-tune each parameter in a very large neural network to arrive at an amazing answer to a very difficult problem. But this is still like pragmatically applied machine learning. As you add more data to this, it's going to perform better and give you better predictions. And that there's no, like for something, if this does a good job, there's no reason to make it more complicated. One of the nice things about a model like this is that it's very intuitive. It's possible to like observe it and understand why it's working and see the internal of it. It's very interpretable, I guess is what I'm trying to say.
And they didn't need anything more than this, probably a target to figure out whether make a lot of money figuring out who's pregnant or who's about to get divorced to buy a couple of key products.
Yeah, I mean, you might be amazed at how often Bayesian show up in the real world. If you've ever used one of Windows diagnostic boxes where you say, I'm having trouble with my printer, and it starts asking you questions, guess what it's doing?
Yeah.
Like, it's just it's a Bayesian net. There are a lot of diagnostic systems that are built on top of Bayesian nets. Your spam classifier traditionally has been a naive Bayes network. Where the features are the presence of certain words. So words like buy or deal or horrible misspellings of common words like would be nodes, and the presence of those indicate a higher probability of spam. So a lot of the common software that you're used to using like has something like this underneath it. So let's talk about the partially observable case. A case where we have data, but not all of it's filled in, or in some cases we can only observe some values. Like, what should we do in a case like this? There are several good options, actually.
You can correlate the variables that you have.
Yes, well, there are even simpler ones. The simplest one is throw out all those rows that don't have all the data, and then do what we did before. Which, if you have very few missing rows, that's actually an okay way to go about it. It's just that it wouldn't work really well for something like the business problem I described at the beginning of the talk, where you have maybe a few hundred questions that you might ask somebody, and one person's not likely to answer more than 10 or 20, right? In those cases, like just throwing out all the rows where they didn't answer all 200 questions is going to throw out all your data, like all of it. There are some other approaches. You could, for example, say, given everything I do know in this row, what's the most likely value to go here? Compute the probability for all the for all the rows that you do have full information on. Pick the most likely value and fill that in. For example, in this case, we're saying it's cloudy, it rained, but there was no sprinkler, and I don't know what value goes here. Well, let's look at all the other rows that have that. That's true here, 1, 1, 0, and it was wet. 1, 1, 0, it was wet. 1, 1, 0, it was wet. It's not unreasonable to fill this in with a 1. Like, that's not a bad approach. We could look at the same thing here. It was cloudy, but it didn't rain, and there was no sprinkler. What happened? Well, we're in trouble now, because there is no other row in our very small data set that has that information. So in this case, computing a probable value for that is a little more difficult.
But you can always correlate the variables so that you do have that are not blank. So
Yes.
the first one, given that it's cloudy and it's rainy, what are the chances that the sprinkler went off?
Right.
You can use that partial row to make your prediction.
You can, although in this case, if our model was built such that we said that wet grass only depends on cloudiness, then we have a few other rows to draw from.
Yeah.
But if we said that wet grass is really dependent upon rain and sprinkler, then we actually don't have any other rows that fill that in this. Actually, we do. We have one right here. So we could use this one instead. 0.
Yeah.
It's very likely that this one's a 0.
Really?
So yeah, that is an approach. Now, if you have lots of missing rows, how good do you feel about filling in a bunch of hard data? This is really probably not very good, because you might think that if you're filling in like more than half of your rows with some hard assignment from the most likely value from the rest of them, you're actually starting to skew like that those conditional probabilities quite a bit. So what else could we do? Well,
You only apply it for part of the graph and not for the whole graph?
you got kind of the right idea. Instead of doing part of the graph, we're going to use part of that entry. We're basically going to give a soft assignment to it that represents a probability distribution just for that node. Based upon, what we said before is that we could pick out all the values that are, all the values out of the entire data set that match it as close as possible and like do a hard assignment of the most likely value. Or we could do a soft assignment by just taking those probabilities and filling that in and say, okay, based on everything else I know, this is 60% likely to be a 1 and 40% likely to be a 0. That's at least a good place to start. The problem is it's hard to count. Although when you think about it, it might not be that hard. If I have this row and there was a 1 here, then I know how I would count it. If there was a 0 here, I know how I would count it. I would say it's 1 times each one of the values in that row. In this case, if I'm 60% sure it's a 1, and I'm 40% sure that it's a 0, then one way you could count this for doing your conditional parameter, or your probability estimation, is to simply count it as both 60% of a row, 0.6 times a row that has 1 there, and 0.4 times a row that has 0 there. So instead of counting up, for example, for wet grass, given these two things, all the values that are 1, you could say, well, how many times that it was rainy and the sprinkler was off did I have wet grass? The answer is 0, 0.6, 1.6, 2.6, 3.6. 3.6 times out of 1, 2, 3, 4. 3.6 times out of 4. And just count that as 6/10 of a row. That's still going to give you, when you total up any missing rows like that, a number that you can divide and get a probability. But instead of like hard assigning it and really skewing the estimate, you're sort of splitting the unknown along the lines of the distribution of the information you do know, and sort of partially assigning it to each category. Now, that's not the end of the story, because you remember the likelihood function we talked about back here, where you were trying to get like some sense of how well all these probabilities fit within the graph. The normal procedure from this point forward is to, given these estimations, go through and predict what the probability should be, right? For the entire set. So total all those up, 3.6 divided by however many there were, and that's your probability estimation for that entry in the table. But then, given that estimation, that actually gives you more information about what should be here, because it shouldn't be like given everything we counted, it shouldn't actually be 0.6. We only counted like parts of each row for that, and then we found out that 7.72 is actually a closer estimate when we divide it up like that. We could then take 0.72 likely to be wet grass and fill that back in for the one that was missing before. So now instead of 0.6 and 0.4, it'd be 0.72 and 0.28. And now we recount and re-estimate our parameters, and then fill that back in as the distribution. And over time, this will converge to the best possible likelihood minimizing function. Or I'm sorry, likelihood minimizing probability set that says, given everything that we know, this is the maximum likelihood for these conditional probability parameters. And you can do that for each one of the values that you're missing. So this is called expectation maximization. And the idea is essentially this oscillation. Estimate your probability, use your probability to fill back in your data that you're missing. Now estimate your probability, now use it to fill back in. Now you might think this would run away, but it doesn't. What actually happens is that with each step, you sort of get closer to a limiting value. And basically you run it until you feel like it's converged, not making much change between each iteration anymore. If you do that for all of them, then even though you're missing a great deal of data, you can do a pretty good job of getting a reasonable probability estimate for each one of those interior values. Now this is not superior to just having all the data. If you have all the data, or if you can get all the data, that's great. But for many cases, it's simply not realistic. Some nice properties about it is that this is monotonically increasing. That is to say that each time that you run the iteration, it may change by a small amount, but whatever it changes by, it will get better. By definition, you're making that likelihood function slightly higher with each step. The downside is that you're not guaranteed to get to the absolute maximum. It's possible for that underlying likelihood function to be sort of wavy. So whatever hill you're closest to, you'll climb that one and stop there. Yeah, it's a local optimum. And there may be a better value out there, but typically it's not going to be much higher than what you're able to climb to just sort of naively. Now, this is not just for data that you're missing. It also can be used to represent data that you don't even have. Now, that might be hard to envision, like, why would we model data that we don't even have access to? But I think I can make a case for it. The general case for it would be something like this. If all you have are nodes that represent something you can observe, and they all seem to have like high correlations with each other, then you're going to end up with a lot of arcs between them. And the more edges there are in your graph, the more conditional probabilities you need to compute, the more complicated your model gets. And in some cases, you know that there is something underlying that is the real cause that you just can't measure. A good example might be something like a diagnostic system, for a differential diagnostic system for something that is inherently unobservable. For instance, there are many diseases that are not necessarily easy to perform a direct test for, but doctors have sort of differential diagnosis charts that say, do they have this symptom? If so, do they have this symptom? If so, have they exhibited this? And they sort of follow that tree down to getting the best possible diagnosis without an invasive test. That's a good example of sort of eliciting a hidden variable. There's, for example, you might not be able to observe that there is like, observe directly that there's fluid in their lungs, but fluid in the lungs might cause several different for example, you might have a very productive cough, you might have difficulty catching your breath, dyspnea, and you might have edema in other areas of your body. If all those three things are true, then you might say, well, like there's something underlying that we're modeling that we can't observe directly, but that we have evidence of. And that can clean up a graph quite a bit to where you're not having to model each one of those directly. The problem is that you don't have any data to fill in each case, right? Like there's absolutely a full column full of empty values. And that algorithm we just talked about previously, expectation maximization, can be used to fill in likely probabilities for these sort of hidden connecting nodes that you can never observe, that will still give you a much cleaner and simpler distribution across the entire graph where you can try to relate all the evidence variables to each other directly. Now, that might seem a little abstract. So it turns out that the business problem I described at the beginning of this talk has exactly that issue. So let's look back at it. Remember, we have many students who we know the answers to many sort of questions about prerequisite information to, but we don't know the full set of questions for anybody. And for our training data, we know some students who have actually gone through these courses and have either done well or done poorly in one of these courses of study. That's essentially what we can use as saying, like, what would be a good assignment. You could think of it as wanting to ask which group of successful students is a new student closest to, most similar to, in terms of their latent knowledge. One possible topology for this would be to draw a graph that looks like this, where you have all your questions. Remember, I only drew 10 here, but there are 200 of them, or 100, but many. And then you just draw a line, an arc, from each one of those questions to each one of the possible credential assignments. Now, that technically is still a Bayes net, but remember that each one arc going in here is an additional factor for binary variables. These are all got it right or didn't get it right, so it's like the simplest possible variable. They all either are 1 or a 0, they got it right or not. Tying each of them to it means having to elicit conditional probability for essentially a further doubling for every additional causal node that you have. So there are only 10 questions here, which means that each one of these requires 2 to the 10th individual conditional probability calculations, and you'll never be able to fill it all in. Like there's gonna, if you have 100, that's 2 to the 100. If you have 100 questions all the way to 100 different conditional probabilities, there's not enough data to fill it all in. You'll, I have a hard time imagining the case where you have sufficient data to fill it all, because you won't get all the permutations won't be there. You just won't have somebody who got the first 50 questions right and then the next 20 wrong and then the further 30 after that right. They won't exist. There's too many combinations, too many options. So this is technically a possibly correct modeling, but it's not a very pragmatic one. It's not going to work. But what if we did it like this? What if we said, you know what, I can't actually measure, like I can't look at someone's brain and say like, you're good at linear algebra or you're not. But I'm pretty sure that's one of the things that's impacting these. Like, the thing that's really being modeled for all these questions is not the relationship between this question and doing well in the course. The question is really asking, are you good at linear algebra or not? And if we have enough evidence to confirm that, then that's really just one bit of evidence that's informing whether or not you would do well in machine learning or artificial intelligence or data analysis. Same for this group of questions. They may all be about Excel or about SQL. And in those cases, like, there's no reason to tie each of them directly. The thing they're modeling is not whether or not someone who answers this question does well at a course later. The thing they're modeling is this latent knowledge, something you can't measure someone's brain and find out, but what really is like the underlying value. And now, just by adding those intermediate nodes, think about how many fewer probabilities there are to compute. Now we can't observe these, we have to elicit them through expectation maximization, but each one of these only has a handful of questions adding to it. That means that instead of having to compute 2 to the 100 different conditional probabilities for each one of these target cells, they each have to compute 2 to the 3. 8 different cells of conditional probability for all the data that we have. This is much more tractable, much more easy to fill in. And in fact, in some cases, you can even cheat. Like the sort of right thing, or maybe the most common thing to do here would be to say, let's fill in all these question nodes, and then use expectation maximization to sort of jump back and forth between estimating these probabilities, using them to compute our likelihood, and re-estimate our probabilities, and like just fill it in and get a better model, and then fill it in and get a better model, and we could do that. But it turns out that these particular questions, like, there are some natural interpretations you don't need to elicit directly. You could do something like, for example, say, this node, instead of being only going 0 or 1, could be simply the number of linear algebra questions you got right out of the number you were asked. And all of a sudden, this graph got much, much simpler, right? We don't even need to elicit these. We can just know the topics of each of our questions and then fill those in directly. So that is my proposed graph for how we could actually model this. And now I'm going to show it to you, because this is a real thing. So let me go back to showing my desktop. There it is. Yep. Okay. Now I'm going to blow through this code pretty quick because it's not the important part, but I do think it's important to show you that like there's nothing really scary underneath of it. All that's happening here is we are loading up data about students who have, we've loaded up data about students who have both been in a program before, one of our machine learning programs or artificial intelligence data. They actually took one of those courses. They either did well or they did badly. They graduated or not. And we have both, and they took a survey. They took a bunch of questions for us, and so there's information there about what sort of things they do. Now, we also know whether they succeeded or not, and we can then say, well, here are all of our students. Now you notice it's not fully filled in. Each one of these is a question number, like from 1 to however many we have, 115 in this case. And 1 means they got it right. 0 means they got it wrong, and nan means they didn't take it. Right? So you can see this is pretty sparse. Like this is not something where really anybody has filled in all of them, or at least not very many of them. There's no way to just do direct. We do have some information about all the questions, and from there we load up the data about what we call their grit scores, or sort of how well they have done or are projected to do in a given course. So the ones who are doing very well. Those are the ones we would like to find similarities between. We basically want to know, well, what we really wanted to say is, given they answered all these questions correctly, and they did well, like that's evidence. If other people answered this set of questions correctly, they're also likely to do well, especially if many different examples exhibit that. Many different students answered this overlapping set of questions correctly and then did well in the machine learning course. This is like one, I think it's only like a few hundred lines of code to look through each different set, and you can see that we're reducing the questions down to which topic they fall into and how difficult they are, and that's it. Like the final model doesn't retain any information about individual questions. It just basically has a count for each topic and the difficulty of the question for how many they got right or wrong, and that's basically the graph I showed you on the slide a minute ago. and that ends up getting serialized into a model that produces sort of joint or offset probabilities like this. You can see that each one of these is a key that represents one of our programs. So they're just an internal value that, like ND002 always represents the data analyst track. ND009 represents the machine learning track, and ND889 is the key for the artificial intelligence track. And you can see that each one of these records in this output is sort of giving you relative scores between for a given person between each one of the possible tracks that could go on. So in this case, if I were to zoom in on that example, I'll highlight it. You can see this person has produced a value that's highest for ND002 and lowest for ND889, which we would use to make the conclusion this person would probably be most similar to the students who did well in the data analyst course, rather than the machine learning course or the artificial intelligence course. So this is the part where we sort of trained it and tried to get a good example of how it performs on our test data. And now I'm going to show you working live. So I'm going to go ahead and query the API for my user who has answered no questions yet. And I want you to look at the probabilities that are present here. This is a uniform distribution because it knows nothing about me. I'm not answering any questions. So it sort of says I don't have any information to decide. Now, under the hood, what's happening are there are sort of three different classifiers there. One for ND002, the data analyst, one for machine learning, one for artificial intelligence. Each one of those computes a value. High is good, low is bad. And they sort of get added together and divided by the sum of themselves to give you a relative probability between them. So these can be thought of as like something that should total to 1, and you can interpret them as saying, what is the probability that this person would do well, or that this person is best suited or most like the students in that target group. And you should see it begin to tilt as I answer questions. So here is my survey. Okay. The formula below is used to calculate information entropy of a discrete random variable x in bits. How many bits of entropy does an 8-sided die with values 1 through 8 on the faces have? Now, since an 8-sided die will be uniform probability, actually that's not important to explain. Let's just answer one, and we'll right or wrong will tell us something. So it's accepted and it's giving me a new answer. Now I've only answered one question. Now look at that. I did not answer it correctly, and so you can see the that already, like, it's got a little bit of information, right? It only knows the answer to one question, but it knows that I got a question about a topic that's common in artificial intelligence wrong. And so it's already starting to tilt away from artificial intelligence and towards data analyst, which is the easiest of the three. So let's do another one. Which of the following must be unique in each of a traditional database? I believe the answer to this one is primary key. Okay, so I've only answered two questions. There are like something like 100 in here. And now that one I got correct. And I can see that like ND002 starting to look like a good fit. Now, why that is that I didn't get it wrong, but I did answer something that doesn't give me much information about these two, right? Like answering a question about SQL doesn't tell me a lot about AI or ML, but it does tell me that I'm likely to do well in the data analyst course. So even though I didn't do something wrong, it's still pushing me towards the lowest one because that's what information it has available. So some calculus. What's the derivative of 5x squared plus 4? That should be 10x. So I've answered a calculus question correctly. Calculus is important or at least a bit of an intuitive grasp of calculus is important for machine learning. And so you can see that's quickly said, wait a minute, like, and drop you back here. Now, the API itself contains some information, like some flags that sort of say, I think I have enough information to be confident now. So like that's some signal to the consuming app that it can stop once it feels like it's a very confident prediction. But any point along the way, it's possible to say, if I only have the information I have now, this is my best guess. For most of the ones we run through this, if they're willing to do 10 to 20 questions, then you can be up in the 70 to 80% likelihood, at least according to the data we have so far. Now, this is something that is going to take some time to improve because right now we only have our training set, and we won't find out about students who are using this and then going into their program for a while until we see how they actually do in those programs. But as you add more data, that makes those probability tables more accurate, should sort of automatically increase the performance of the model over time without having to change anything about the code. That is the learning portion. The more that you feed through it, the better it should be able to do, provided that we don't have any underlying issues like overfitting, and there are a ton of possible ones like that. But sort of understanding the internal sufficiently to be able to diagnose those is sort of a different topic.
Would you, is there any analysis going on here, or could you add analysis to say, hey, maybe we have the key wrong, we're grading this question wrong, we got the wrong answer, because all of a sudden, we got a lot of people answering this question that are supposed to be smart in this area, they're getting the wrong answer.
Well, so there are various types of error analysis that are common to do on sets like that. One is sort of the very coarse-grained level, where you say, we made some predictions that this set of people were going to do very well in the AI nanodegree, for example, and then some percentage of them didn't. Now, you're not going to get everything right, but it's worth looking at the ones that the model got wrong and saying, is there a pattern here? Because it could be that there's some underlying variable that's not being well modeled. Now, for example, I know one that's not being modeled here is like, how thorough is this person? Like, you can know all the underlying information and just not have very good study habits and still do badly. Like, the prerequisite information is not everything. It doesn't like deterministically determine who's going to succeed or not. So there are certainly like missing values here. Some of those are beyond our ability to measure, but some might not be. It may be that we've missed a subtopic that would actually give us a lot more useful information. If it turns out that many people who are good at linear algebra but didn't necessarily have a good geometric understanding of the underlying principles still didn't do well in AI, well, maybe we should introduce some questions that measure that more directly. And that sort of measure somebody's intuitive understanding of what an inner product is, or of what sort of linear transformation a matrix multiplication operation represents.
With your data set, you're just doing the ones where they answered successfully or unsuccessfully?
Correct, yeah.
But would you also be able to use that they did not answer, that I don't know?
That's great, yes. Now, we're not using that now, but we have a suspicion that those give you more than just data about right or wrong, right?
Right.
Like, they might also indicate a certain level of confidence, and people who have a low degree of confidence will typically do better on an easier track than somebody who's quite confident and feels like anything standing in their way is something they can just beat down the door on. So like there may be signal here. We don't have data that indicates it yet, but it's a really good intuitive leap, and it's one that we're thinking about. That yeah, both the I don't know signal should maybe be measured differently than the just answer it wrong signal.
Right.
Yes.
The probabilities start off at 33% for each of them at the beginning. Like, for
Right.
example, if you only have 10% of the people in the wild are artificial intelligence, shouldn't it start at 10%?
That's a good question. I guess you're saying like this is the uniform distribution is not the true underlying distribution of who ends up where. The reason that we felt like uniform was appropriate in this case was that the client apps that are using this information to sort of make decisions can sort of make some of their own decisions about the thresholding and decide at what point to say we've learned enough. And we don't want to put somebody in the position of having made their threshold too low and misimplementing it by just asking immediately and saying, oh, we're throwing everybody to data analyst because it was 80% confident. So it's a good point. The correct underlying distribution is not uniform. And it would be more theoretically accurate to maintain it that way. But we decided instead to represent it as uniform to convey to perhaps a slightly less numerate consumer that like we have no information yet. This is the best we can give you based on all the information we have now. Additionally, it turns out that in this case, our training set actually was uniform. So although the underlying distribution of all the students is actually rather skewed, we intentionally collected a uniform set of a few hundred students from each one of the programs. So the data that the algorithm knows about is actually uniformly distributed up front. But it's a really good observation. Yes.
Is it helpful to chunk it? So like, say you've had the data analyst course around for 5 years, and all of a sudden now you're going to decide to bring on machine learning and artificial intelligence. Do you get a better model if you have chunks of it with a lot, can you build these Bayesian networks from bottom out?
Are you asking if you could append to them later, like make them wider later? Yes, certainly. And in fact, what I would actually say is, although I've drawn these as one graph, I would actually consider these 3 separate models. Each one of these on their own are in their own naive Bayes network. And you may hear that term because the naive Bayes is a fairly common model. If you ignore these two and just look at this, there's only 3 arcs to it, right? From each one of the evidence nodes to the sort of target node. Any idea why that might be called a naive Bayes model?
Independence.
Yes, absolutely right. Yeah, A naive-based model only ties the evidence directly to the target variable and has no relationships between any of the evidence variables. It's naive about whether or not those are actually conditionally independent. For example, is it really likely that linear algebra and calculus are entirely independent and that if you know one, it doesn't tell you anything about how likely you are to know the other? No, absolutely not. If you know if you know linear algebra very well, you're very likely to know calculus. If you know calculus very well, you're still slightly more likely to know linear algebra. We know in the real world that they are likely related. However, given that each edge that we add to the network increases the complexity of the model and increases the number of conditional probabilities we need to elicit, there's some trade-off between adding complexity, even if it represents underlying truth, and whether or not that really improves your accuracy. So this is actually a really common problem in all statistical and machine learning modeling. Adding complexity may give you what feels like a more right representation, but if it doesn't actually perform, give you a better prediction, if it doesn't actually improve your accuracy, it's additional compute power for no results. So there's sort of, I was going to say an art, that's not really quite fair because there are like good rigorous methods for sort of plotting the pattern of how a model evolves when you add complexity to it and deciding whether or not it's gone too far or not. But there is a little bit of intuition behind deciding what things to include and what not to include, especially if you're eliciting a structure manually like this and sort of saying, I think these things should be related. For example, back in our DevComo net, there are a lot of other things I could add to that might be relevant. For example, inclement weather might be a reasonable one to add. I think that whether or not you have kids may have some impact on whether you're likely to speak or not, because you may be less likely to devote time to being a speaker if you have kids at home. So you could draw a lot more edges that I think would be reasonable, and you could justify them causally and say there are underlying reasons in the real world why these things are related. But if they don't give you more prediction accuracy, you're doing a lot of extra computations for perhaps not much benefit.
So you're analyzing your nodes to see if you're getting basically too small of a number?
Sure, so what you can sort of do in a case like that is you can say, here's a model, one that I know does fairly well, and you can look at a set of data that it didn't train on and say, how accurately does it categorize each of those? Maybe the answer is 70% of them it gets right. Now, I think that I know that this other node, I think that I know that having kids impacts whether or not I'm going to be a speaker. If I add that edge, recompute everything, and recheck my accuracy, it might be that now my model is 75% accurate. Well, maybe that was worthwhile. But if it turns out that nothing's really changed, or that perhaps it's gotten worse, then which can happen in cases where you add sufficient complexity to the model that it really fits to only the data it's seen, it sort of memorizes the training set, then it's possible for its generalization to data it hasn't seen to get worse. So those sort of objective evaluation metrics that occur after you've sort of built it can help you make a decision about whether or not adding complexity or reducing complexity has really made any difference at all in predictive power. Yeah.
What happens if you have an outside point of data that's not part of the calculation that throws it off? For instance, you're looking at the likelihood somebody might make a purchase, but you don't look at the factor of how well, say, the economy's doing, and the economy goes bad, and all of a sudden your machine learning is no longer predicting. It's learning that change, but how do you...
It may not learn that change.
How do you detect or capture that you have a problem quickly?
Some of this depends on the model. Okay. There are many models that sort of encode temporal locality. That is to say that they don't just base it on sort of broadly available data, but also what was true yesterday. And in those cases, you can sort of weight recency as being very important. That is to say, if you have many training examples, it's possible to sort of weight how important they are, or even throw them out after a while. In cases where a model might be subject to economic swings, it might be reasonable to say that you're always just training on the last 2 months of data. And that's it, because data older than that may have sufficiently changed underlying conditions that you just can't measure reasonably, and data relevant to now. The weather's actually a really great one. What are the odds that it's going to be 20 degrees tomorrow given that it's 20 degrees today? That's a lot better than just trying to do, pick a random day on the calendar, right? And so those are cases where temporal locality can have a lot to do with it. In a model like this, you can do that by saying, making yesterday's temperature a node and explicitly encoding recency. But there are also cases where I guess what I'm saying is there are many different types of machine learning models, and each one of them is meant to encode some sort of bias that says the practitioner believes that these things are important to represent. In something like a Bayes net, one that's structured like this, the bias that's being encoded is, I think there are only a few real relationships that matter towards producing a result, and that it's sort of like something that's true for any given case, irrespective of time. There are such things as dynamic Bayesian networks that exist in time steps. A common one would be a hidden Markov model, or there are many others like that. But they're essentially cases that have like a Bayes net that represents a moment in time, and then a Bayes net that's the same model structure, but like represents the next time step and is somewhat dependent on the nodes in the prior time step. And like each step, it could be a day or it could be a minute, but each step is basically a new inference that is based both upon all the things you can observe and what you knew yesterday. And in some cases, if recency matters a lot, or if more than just one step in the past is important, you can have dependencies that you can have edges that tie back 1, 3, and 10 steps in the chain. Keep instantiating forward. Those are a little complicated to include in this particular talk, but whatever, or for many of the common types of what if I have this sort of data-shaped questions, there is some variant of a traditional model that is sort of built to encode that sort of bias. It's broad, though. Yes?
I had a question about your assessment. So I gather in your item bank you must have like, what, 200 questions, but you don't ask all 200 questions because they'll drop out. They're not going to do that.
This is a super good topic. I'm so glad.
So let me follow up on that. So have you thought about making your assessment adaptive?
It is.
In other words, the next question you get is dependent upon the answer before, and I've taken exams like that.
Yes.
Microsoft did that.
Yep.
They did that on an MCSE exam that I took too many years ago. You sit in front of the computer, you paid money to take this test. You sit in front of the computer, it gives you a multiple choice question. If you get that one right, the next question it gives you is a little harder. And if you get that one right, it's a little harder still. If you miss one, it drops back a little bit. And it scared me the first time I did that, because I paid money to take this. You gave me like 10 questions, and they kept getting harder, and a little harder, and a little harder, and then all of a sudden I'm like, I'm not sure about this one. And so I thought, well, this is my best guess. And then the computer says, thank you very much, this exam is now over. And I'm like, well, did I pass? What did I do? So I walk out the room, and the printout comes out on the printer, and the exam administrator says, oh, congratulations, you passed.
It was fast.
Like, really? That's only like 10 questions.
Yeah, so I guess what you're describing there is, in some cases, it's possible to like optimize for the number of questions being asked, right? And sort of say, like, can we get the information that we desire in the fewest number of questions? The answer is yes, and in fact, I didn't get a chance to discuss it, but that is what's happening, but although not the way you're describing. The thing that's being targeted in an exam like that is whether or not you are competent in the underlying material. That curriculum is the important target variable, right? It's trying to determine, like, you need to know this set of things to pass the exam. Do you know these set of things? The question being asked here is slightly different. It's not really, do you know linear algebra or do you know calculus? The real fundamental question is which group of successful students are you most similar to? And so it's very possible to have that be like slightly askew from whether or not you, like they're sort of pointing in the same direction but sort of offset from the question of whether you know the material really well. So the way that this quiz is adaptive is by trying to ask the question that will give us the most information about the thing we care about, namely the body of successful students that this candidate student is most similar to. And the way that it's done in this case is by saying everybody who has taken it up to a certain point was given a random set of questions, right? Now, that means that not all questions have been answered in equal number. Like there may be some questions that have had 100 people answer them, and some questions that have had 20 people answer them, right? Now, the ones that have had many people answer them are sort of intuitively a little more predictive because you have more signal about that question with respect to whether or not that represents the student body, but only if it's balanced among the various classes. So if you had 100 people answer one question about linear algebra, but they were all in the machine learning course, that's not as helpful as perhaps a question that 60 people have answered previously, but that had 20 from each one of the various candidate courses. So there's an underlying equation that essentially is something like take the absolute number of people who have answered this question before, for whom we know their outcome, and divide that by, or essentially multiply it by a weight that's determined by the balance across the various degrees. So a question that has many answers and also has those from a sort of uniform distribution from the various degrees, that gets weighted very highly. And then you have those, basically take those weights for all the questions that the student has not answered yet, and divide each one of those weights by the sum of all those weights, and that gives you a sort of ad hoc probability distribution, where the ones that have high weights have a bigger probability of being sampled. You linearize those and then like sample from it, just say, pick a random number between 0 and 1, and look within the index, and like each one of them is sort of a different width in that index depending on how highly weighted they are, and whatever one you land in, that's the one that's going to answer the next. So it doesn't deterministically pick the next one, but it sort of gives you a higher likelihood for being sampled with questions that we think will give us much more information about which student group you'd be similar to. So for example, a question that no one had answered before, no one would ever get asked. It would have 0 probability of being exposed under that system. Which is not quite the same type of adaptability, but there is a little bit of cleverness with respect to which question gets asked next.
Okay. And are you looking at things like, suppose you do extremely well at SQL and Excel and all those questions, but the students drop out because when they take the data analyst course, they're bored to death.
Yes.
It's too easy. It's not that it's too hard, it's too easy.
So we think that would be captured because if it were true that students who broadly do well in all of the prerequisite material, like all of it for data analysts, would then drop out of it, that would be present in the training data. We have a group of students who did successfully who are doing well in data analyst. If they were going to drop out, they would have done it. And so it appears that at least for that group, it's not the case. There are also plenty of students, if that is true, and if they would do better in machine learning, then that would be shown by students who are currently in the machine learning degree, who didn't necessarily do very well, might have done okay in calculus and linear algebra, but did very well in SQL and Excel. Like it's still it's possible for that to be true, and if it's true in the data, that's what we'll predict. And that's why this is different from asking the question, are they good at these topics?
Yeah.
It's really asking which student group are you similar to.
Almost similar.
So if students who know everything in the prerequisite list for data analyst do poorly in data analyst, we would not predict them to go there. We would predict them to be with the student body that they most resemble, who have done successfully in whatever course of study they chose. It's still a possible flaw, but it's one that we have thought about.
Yeah, so I don't know if I missed it before I came, but when you, how did you know that your Bayesian neural net would be more useful than just a general purpose neural net? Like what about your problem set gave it away that this would be a useful topic?
Totally. So because one of the reasons it's good in this case, actually there are several reasons. The first is there is not really sufficient data volume or complexity to justify a really complicated nonlinear model. And we have a certain requirement of interpretability in this case. If someone says, why do you want me to go take data analyst? I don't think that's right for me. We want to be able to have a pretty good answer of why. And being able to say, well, our algorithm said so, is kind of cool for some people, but others would go, well, screw your algorithm. That's not what I want to do. So a Bayesian network in this case preserves some degree of interpretability. We can look at the output and say, you were assigned to machine learning because you did very well in linear algebra and in calculus, and not so well in discrete mathematics. And discrete mathematics is something that we think is important for the AI nanodegree. Now, because a deep neural network is fairly powerful, it would certainly be possible to fit to this data set, but it's computationally more intense and less interpretable, and therefore probably not a great fit for this problem. Now, if we were trying to do something that had a great deal of data, for example, we have other models that try to do things like say, given everything the student has ever done in this course, how likely are they to graduate? That would probably not be a great fit for a Bayesian network because every single video they watch is a data element. And trying to map that as a bunch of nodes would take a long time to learn the optimal structure of, and it's still not very interpretable because there would be thousands and thousands of relationships in there. There are, in some cases, many, up to 3,000 or 4,000 nodes within the linearized view of a full set of courses. So that would be a good case where something like this would not be a very good fit. But when your dimensionality is not very high, and when interpretability is fairly important, then this is a pretty good fit. Additionally, this is also a case where the data is not very fine-grained. The only things that we know are the answers to these questions, and we know that's not all the data that really informs whether or not a person is going to be successful or not. There are many other things: family situation, career background, academic background, several personality traits that just determine what kind of a good student you are. And so, like this prediction of do they know this stuff, will they be successful? It's noisy already. Like if we had all of that data, then a very complex modeling might make sense because we can make use of all of it. But like the data we have is just not very rich.
I just have maybe a little bit of follow-up. Is kind of the implication of that then a general neural net might do better, but because we have other requirements, we chose not to use it? Or is it that the general neural net probably wouldn't do, or it would be very comparable to the Bayesian net?
I'm not convinced that it would do better, but that's not because we tried it and I found that out for sure. So I can't say with certainty, like, no, that would not do better. I have some intuition that it wouldn't for a couple reasons. First of all, deep neural networks can fit very complicated hypotheses, and as a result, they tend to overfit their underlying data sets. It's possible to control this with regularization, things like very small lambda parameters for each one of the weights that are inside the nodes, or just using dropout or something like that. It's possible to control for it, but like that's going through a lot of song and dance to essentially say there's not enough data here to represent it very well, so don't care very much about the data. This is a model that has some high bias built into it already, because we're essentially saying we believe that these things are the underlying values that we can get at right now. And when the model is that intuitively clear and the volume of data is not very high, it's not that it's necessarily going to for sure fit it worse, but my guess is that there's not sufficient information in this data set to do a lot better than currently exists. If that makes sense. Yes?
Wouldn't it be easy to test? Just do tenfold cross-validation on
totally.
this model and a deep neural network.
Totally.
Yeah.
It is easy to test. What that comes into is sort of a question of like how valuable is people time, right?
Well, deep neural network's pretty easy to set.
Sure, it is fairly easy to set up, but when you get like the people time isn't just in setting it up. It's also then in saying, okay, we have a 1% difference. Now we get to have a meeting where we decide whether or not that 1% difference is really worth making it really worth making the leap. And there are going to be a lot of opinions. So I guess my point is that based on the prior criteria for this particular problem, we have achieved sufficient performance for the moment. It can be a lot like performance optimization, actually. If you want to make something fast, then you can say, I can think of a lot of ways to shave off a few extra milliseconds here. We might say, those are all good ideas, but we're not really concerned about those milliseconds right now. Like, what we have is good enough for the moment, and we want to invest our time elsewhere. Because it's not just the how complicated is it to set up. Like, it takes people time to context switch between tasks. And particularly opaque tasks where the payoff isn't very clear, like, you have to be pretty ruthless about prioritization when there are a lot of different strings pulling at you. So given no other constraints, given no resource constraints, no people constraints, I think it'd be perfectly reasonable to say, look, we got a whole toolkit of stuff. Let's throw every algorithm we have at it and see if it makes a very big difference. But at least experientially, from anecdata, I could tell you that the choice of algorithm is not. Oh my gosh, these move. The choice of algorithm or model may not be as important as getting a really good encoding of the data, something that actually represents the thing that you believe is the underlying causal factor. A lot of the variance in performance can certainly be based on statistical noise. So, like, other than really demonstrably large increases in predictivity, it's not even guaranteed that a small gain would really be one that would pay off in the general. But like, given the time, no reason not to do it.
If people want to catch up with you after the meeting, what's the best way to do that?
I've got nothing else going on tonight, so you can come talk to me here. I also am, let's see, I really cut off a lot of my social network stuff. I guess I'm on LinkedIn, and I do check that periodically. I'll be here next month. I should put my email up there, I guess.
You could just post it to like a DevComo. Like,
I will post
Slack
my
channel.
email to what?
Our DevComo Slack channel.
Okay.
If you're not on there, it's a network and group of like amazing people that just kind of comes in and solve problems every day.
All right, Tom will show me how to get on the Slack, and then.
Go to devcomo.org right now.
Right now?
Yes. We're doing this.
Everybody else pay attention. This is how you get on the Slack channel.
All right, so you're going to join the group via Meetup, or you can give a talk, and then at the very bottom, scroll hang out on Slack. There you go.
Access
Get
here.
access here.
We need to make that anymore.
Nabil.
It's a good thing you knew it was there because,
Yeah.
So if you click on it, it should take you to Slack.
oh, I clicked it.
You just sign up. It's going. It's slow.
I'm fully confident this will work eventually.
It's good.
Everybody else do this too.
Make
So you mentioned the word interpretable. Does that reference, like for instance, you train a neural net to play a game and it gets better at the game, can you look at the weights in the model and say, this is the way I can become a better player, or this is the way I can play a better game? Or is that...
There it is.
Yeah, excuse me. I'm trying to kill you.
So in the particular example that you cited, I think that you would do better to learn how to play the game by simply watching the output and watching it play the game, like on a physical display and learning from that. Now, that's not to say that deep neural networks are entirely opaque. They're not. But if you think about what's happening under the hood, like you're learning intermediate features along the way that represent nonlinear transformations of the original vector, and each one of those is a combination of like all of the nodes before and like some particular weight combination, right? So being able to interpret what each one of those really mean is hard. It's doable. You can look at any one node in a hidden layer and say, like, look backwards. What are all the weights that fed into that, and which ones are big? Okay, so like that one. Now, if I look at the layer before, then like depending on the number of layers you have, this can be very tedious, right? There are other ways to do it that are a little more black boxy. You can do something like what's called ablative analysis, where you essentially do things like, if I tweak this parameter a little bit, how does that change the output? If I like take a bunch of training examples and only change, like just nudge bits of inputs one way or the other, how does that change the outputs? There are ways to understand how, like what it's modeling underneath, but it's not. Like you're still only sort of getting an approximation, right? Whereas there are many models like Bayes nets, like logistic regression, that do pretty well on tasks that don't require that level of complexity, and where you can give a very confident answer as to why the model made a decision that it did. So it's not the same as saying one is interpretable and one is not. It is a continuum. But for problems that are of low dimensionality, like this one is, and that don't and that require a certain amount of interpretability and being able to answer the question afterwards. Anything that has to do with people's fate, I think, often requires a certain degree of interpretability. Like this is a sort of minor one, but there are algorithms out there that are involved in like sentencing decisions or in risk for future recidivism or treatment options for somebody who's got an advanced disease. And in those cases, I think interpretability is going to be required for a long time, whether we like it or not. Just legally, it's going to be. And so knowing which tools in the toolbox fit that requirement, I think, is useful.
Get your case heard right after lunch.
Yeah.
Good predictor.
Yeah.
All right, let's everybody else thank you then for coming out and presenting.